So, coordinate systems, the ones we've looked at so far, pretty much are describing what happens with vector data. So, let's briefly look at what happens when we're handling raster and we have to apply coordinate systems to them, raster data sets. The same general idea can apply where you have an origin point somewhere on the Earth's surface, and then you're measuring locations north, south, east, and west of those. But in terms of a raster, all we really need to know is the location of like one point for sure on the Earth's surface. And then if we know the cell size we're trying to draw, let's say 30 meters as a cell resolution, from that origin point, we can just draw these little squares, 30 meters on a side, and then we can store in our data set how many columns are there, how many rows are there. That tells us how many of these squares exist east and west. So the rows are going north and south, the columns are going east and west. So if we know the cell size resolution, we know the origin point, we know the number of rows and columns, we can draw any size raster grid from those. Okay? And as long as that X and Y location is fairly well georeferenced to some actual location on the 3D surface, then our raster is necessarily showing us um, properties of the Earth's surface given the limitations of raster data, but also showing us those data linked to spatial coordinates. Here we see South Dakota shown in two different coordinate systems. On the top, geographic coordinates, unprojected, straight degrees, minutes, and seconds. And on the bottom, South Dakota done in a state plane coordinate system, which has measurement units in meters. And so the shape of these things is very different. Similar, but different. You can see the configuration is altered quite a bit between the state plane coordinate system and the geographic coordinate system. Remember that geographic coordinate systems are being displayed more or less like cylindrical projections. So we see more and more distortion of area as we head northward because those lines of latitude are parallel to each other as they head up north and south. So that introduces a lot of stretch along the northernmost portions of any map using geographic coordinates. So the South Dakota State Plane is being drawn, and it looks like those lines of longitude meridians are going to converge at the North Pole. And so it's doing a better job of describing those locations and the shape of South Dakota as it exists on the globe because of that fact that those lines of longitude are converging as they should at the North Pole. Okay, and so see, Price has this other note in here. Their paragraph, you can change the XY value in the upper left corner. It doesn't affect the underlying shape of the actual coordinate system defining this thing. Okay. Um, Typically, you're not going to go in and change a lot of coordinates on a raster unless that raster is damaged. You know, you're not going to worry about doing that. Pretty much what you see is what you get. Earlier in, meaning about 20 years ago, when rasters were not as well developed as they are now, we actually had to go in and we would get raster information in several different files and we would have to combine them. And in that process of combining the files in order to generate the raster, we could do the actual manual alteration of the data and change a little bit um, what came in the output, and that's what she's referring to here. It's not something that you're really going to have to worry about, though. In modern rasters, most of them are going to be generated properly and have embedded coordinate systems already. Um, but just like with vector data, we need to be aware of what that system is, what type of distortion it inherently carries with it that's going to influence the data set we have, whether it's vector or raster data. In this case, we know that a geographic coordinate system is going to have more distortion to the north um, than it is to the south with a data set coming from the northern hemisphere. So you see that distortion play out quite nicely if you compare these two data sets. The state plane is just doing a better job of describing where things are in the data set to what they actually look like location wise on the Earth's surface in reality. So if we zoom in on things, we can get what we're calling local rasters. So portions of larger areas. Still, you think of it like a study area. So we can have a smaller area within South Dakota. Here, two examples based on UTM Zone 13 North or South Dakota State Plain. We can still see differences there, even zoomed in to a smaller portion of the data set, where the UTM Zone 13 is a cylindrical projection, and it has those parallel lines of latitude and longitude, as well as latitude. But the parallel lines of longitude mean that we're going to see more distortion to the north as it stretches those cells out to fit within those parallel lines of longitude. With the projected data and converging lines of longitude, converging meridians, we see a better representation spatially of the data with the South Dakota State Plain. So even though the raster data itself may only know the origin point of the upper left-hand corner of the entire thing, we still need to know the properties of the coordinate system and how they're distorting the data, and how rasters, although they look like they're fine, okay, remember that what we're really interested in geography is matching our data set coordinates to the actual topography and actual locations on the Earth's surface as well as possible. We want that to be as accurate as possible. So UTM Zone 13 might have some properties that are really good for certain studies, whereas the South Dakota State Plain South, for this particular study area, may have superior properties. That's something that you need to make a decision upon as you know and learn what those properties are and how they apply to interpreting the results of your GIS analysis. And that's something that comes with time. It comes with experience. It's not something you're going to necessarily master just in this one class. Okay? But you're going to build that knowledge as you work more and more with different coordinate systems for different areas and see how they introduce distortion. And then you'll come up with your own decision as to what kind of distortion do you prefer to accept, what kinds of distortion do you prefer to not accept, and that will help you make decisions about which projection you're going to use for projects if they're not determined for you already, either by your supervisor or by the details of a contract or an agreement that may specify which projection that you're going to use for any particular study that you undertake. Most of the time, the rasters that you receive for work or that you obtain from other sources will already be georeferenced, meaning that they will already have latitude and longitude values or UTM values applied to them through their coordinate system. Occasionally, you will receive information that you may know what the coordinate system is. It's not labeled properly in the data set, and so you'll just need to go in and manually make some quick changes to make that display properly. Very, very rarely will you encounter a raster that has no coordinate system, a raster that someone generated, but they didn't generate it with coordinates at all. There is a way to get around that, and that is if you have a data set for the same area and there's some way to compare the two so you can tell which locations are which on each one, you can draw the information from the georeference raster and apply it to the ungeoreferenced raster, and then you can transform that raster so that it now has that coordinate system. The process of changing a data set from one coordinate system to another, if it didn't have one already, um, is sometimes known as rectification or georectification. So we take that data set that doesn't have any properties whatsoever, or maybe it has a different coordinate system to it, and we want to change it, we can apply this rectification process, which is done by a process of selecting a number of point locations on both data sets. The original, which doesn't have any data, maybe it doesn't have any coordinate system at all, and then another one. So we can draw point locations between those two and apply them to the original unprojected data using either affine second order polynomial, third order polynomial equations. And so these are regression equations, essentially. If you've had enough statistics to have gotten into regression, this is a regression process. So the higher order progressions introduce different kinds of distortion to the data, and not necessarily what we're looking for. Um, on the third order polynomial, that may be a little bit too much warping, especially along the margins of the data set. But the higher order transformations require more of what we call control points. So you have to do more pair matching between the original and the raster that has the geographic coordinate system. And so it just requires more work to do those higher level transformations. And then your output data set will be imbued or written with the target coordinate system. So you can do rectification from data that has no geographic coordinates. It's a way that you can transform data between coordinate systems. You can also use, if you have a raster with a coordinate system, you can use the reproject raster tool to project it into a different projection system. Okay, so there's multiple ways we can do this. But if you ever do come across that rare instance where you have a raster with no coordinate system whatsoever, there is this process by which you can apply a coordinate system, and you are learning it in at least one of the exercises in the Price workbook. So how this thing works in general, if you haven't had a regression class, is it's looking at control points or linked pairs of point locations between the two rasters, where they are on, in this case, map X and map Y. Okay, where the source locations are on the source map, X and Y. And X and Y are referring to latitude and longitude, I'm sorry. The source map and the map you're trying to produce and project. And they look at where those coordinates are inside the pixels of each raster. And then it calculates for you up here the total root mean square error. So in this case, it's given in the number of pixels. So the total RMS error on this particular projection or rectification is 0.02 pixels, which is pretty good. I mean, less than 1 pixel. That's ideal on a rectification or reprojection. It means the error between when you apply the projection equation is very low. Okay, so that's a good thing. All right, so as you do a rectification process, this table here that you see on the slide is something that you will generate automatically in ArcGIS, and it will keep track of each pair of point locations and how much error is being introduced by each point. So if you wind up with a really horrible RMS error, it'll indicate which of those point locations is contributing more to the error. And so you can delete that point from the projection, and then select another one and keep going and get more and more points and get a pretty good equation that you then apply to the raster to get a very well projected data set into whatever coordinate system you want to have applied to that data set. All right. When we change coordinate systems or cell sizes for a grid, one of the things that typically has to happen is resampling, going from one cell size to another. In this case, what we're looking at is we're taking a higher resolution raster and converting it into a lower resolution raster. So we have to come up with some way to transform the geometry and transform the values. So the color raster is the original. The outlined 3x3 cell grid is the target. And so we're transforming a 4x4 cell original into a 3x3 cell target. And we have to figure out, how's that going to work? How are we going to pull those things off? The geometry is fairly easy to do. And the system handles that pretty well. But one of the problems that we face is, where do you draw the value if my target cell is overlapping 4 different cells? Which of those original cells gives me the value that fills the new cell? Okay, so take a look at that upper part of the diagram where we're overlapping the 3x3 grid over the 4x4 grid, and you can see kind of a problem. Where do you draw the values for the new center of the new cell? And that's kind of what resampling does for us. Okay, it's not only the spatial resampling from maybe, let's say, going from, what is that, about 10 meters to, let's say, 15 meter cell sizes. Okay, that's a fairly easy thing to do, but which value out of those original cells that our target is overlaying contributes to it? So we have choices. And the choices that we have during resampling are these 3, typically. Nearest neighbor, so it'll grab the cell value from whichever original raster cell is closest to the new center. So take a look at that upper diagram, and you can see in the upper left-hand corner, the new cell center is that dot within the center of the larger cell, and it's grabbing from the gray one. So whatever value the gray has, that's what it grabs. In the upper middle one, it's grabbing from the lighter orange, because that's where the center is. In the upper right, it's grabbing from the brick colored cell. Okay, so it's grabbing literally the nearest neighbor. What's closest to my new cell center, it's going to take it. Okay, the second row, it's taking that light purple. Then the middle one's taking kind of the lighter green. The one on the right is taking the lighter orange color compared to the brick. Okay, and so forth. Bilinear resampling, the second method, is one that takes a neighborhood of cells. So the 4 closest cells, it's going to measure the distance between the cell centers and incorporate the value of each of those cells, and then it's going to calculate distance weighted values, kind of like an average between those things. But it's incorporating space, the distance between them, and what the values are in order to calculate that new cell value. Cubic convolution typically does a 16-cell neighborhood, and then that calculates the target cell. So it's drawing 16 different values of distance, 16 different values of what the original cell value was in order to calculate the new cell center. Okay. So nearest neighbor is really good for categorical or nominal information. So like land cover types. Is it classified as a deciduous forest or an evergreen forest or a grassland or urban or something like that? Best for those types of things. Bilinear resampling is best used for continuous data. So elevation, precipitation, temperature, things like that. This is the best one for that. Cubic convolution, it's best used for continuous data, but I'd recommend against using it at all unless the research protocol that you are following specifies cubic convolution be used. And the reason for that is that cubic convolution or similar types of processes, they really smooth the data out, meaning they really hammer down the mountains and they fill in the valleys as you apply it across the landscape, using elevation as an example. It really hammers the extreme values and makes more of a smoother average value in there. Sometimes that may be appropriate to use, but again, I recommend against it unless your research protocol specifies it. For most surfaces, bilinear resampling is more than adequate and very appropriate to use. Okay, so these three are what you have access to when you resample. Whenever you encounter resampling processes during raster analysis, often that's during reprojection, sometimes it's during other types of analysis may incorporate resampling. And so whenever you see that on a tool dialog, then refer back to these ideas. Which one is more appropriate for what I'm doing? If it's a surface, bilinear. If it's not a surface, nearest neighbor. Cubic convolution, rarely ever use that.